Hello, my name is Spike Martin. This is Sam Janoff, Larson LeDuc, Rachel Crispin, Christina Clausen, Parker Heiberg, Jonathan Strang, and Tim Zoller. We are all part of Team CLEO, which stands for Clean Low Earth Orbit. We are working on Project Toad. That's a Targeting Orienting Actuating Device. Here's our beautiful team logo. So, the goal of Toad is to create a system that will orient itself to a target using the reaction wheels, which we'll go into more detail later on. And the original goal was to build an orbital debris mitigation or reduction device. We kind of got the idea from looking at cool things such as Space Fence from Lockheed Martin, where they have a database of all the orbital debris in low Earth orbit down to the size of like inches, which is a really interesting concept. So we wanted to design something that would orient and then remove that debris. However, due to scope and time, we decided to instead focus on the attitude determination control portion. So we're just trying to make something that will rotate towards it using a linear quadratic regulators control system, better known as LQR. We'll then, once we're closer, use our secondary control law, which is an optical control law, which focuses on the target and then determines the Quaternion difference between the two so that it can input a new target to the system. We went through several design iterations, with the one on the left, until realizing that it was an inverted pendulum, which was not quite what we were going for. We instead changed it to the following two, which were shot down due to safety reasons because reaction wheels were not properly housed, until finally settling on the final version, which as you can see has been fabricated. The process of Toad is to begin by stabilizing our initial location, initial orientation. We'll then read sensor inputs from our inertial measurement unit, better known as the IMU, this records angular velocity and angular acceleration. We'll then read the next target orientation from our Raspberry Pi that communicates with our FPGA, which is where our control law is located. We then process the input through our control law and then actuate with the signals sent from the control law to the ESCs to the reaction wheels. Reaction wheels spin, they actuate the system, and then we continue to update our location throughout the process with our IMU and eventually our camera once we're close enough. Eventually we arrive at our desired orientation, and then we restabilize till further inputs are given. Here is a video demonstration of our system rotating through the use of a remote control. To rotate around the x-axis, we rotate the two adjacent reaction wheels in one direction and the two opposite pair in the opposite direction. Eventually we'll get to the y direction. We have two opposite pairings of reaction wheels spinning one direction and the opposite pair spinning the opposite direction. And then once we get to our z, here you can kind of see better on the bottom here, our optical sensor, along with our two onboard cameras. For the z direction, it's much easier. All we have to do is spin all the reaction wheels in the same direction. So what this is demonstrating is that we are fully capable of spinning in all the orientations that we desire. However, in the next slide, we'll show the video where we are attempting to use our actual control law to control the system as opposed to remote control. Just click out of the video. So this is when we were trying to use the control law by itself. Now, you can't quite see it, but they start slow and they quickly ramp up. And so what we think the issue might have been is that our inertial measurement unit was not reading the correct data. This was slightly confirmed through checking the registers later on. The Quaternion data, as well as the angular velocity data, said that it was moving at 1 degree per second when it was not moving at all. That is clearly an issue. The other possible issue is that our gains were not large enough, and so it was not able to overcome the disturbance torques that we did not account for in the system, such as the ball being imbalanced and our individual modules being unbalanced. I'll now pass it off to Christina to discuss subsystem introductions.
Thanks, buddy. All right, so I'm going to go a little bit in depth. Toad is made up of 4 different subsystems. We've got our structure, which is split into 2 modules, and they house all of our components as well as mount to the test bed, as you can see. We have our attitude determination and control, which include our actuators, as well as our 2 control laws, so our overall control law and our optical. Then command and data handling is all the wires and code used to let all those components speak to each other. And then our electrical power supply powers the whole toad. So the structure, here's the two modules. So module 1 has the 4 reaction wheels. They're mounted on polycarbonate sheets and then with 3D printed corners to hold everything together. And then they're wired through the ball, because it's hollow, to module 2, which is the brains, has all the other components, which are also mounted on polycarbonate sheets. So the ADC subsystem, the overall control law was first built in Simulink, then transferred to VHDL, and you can see a simulation run here. And then that's the camera we use for our optical portion. And then our reaction wheels were off-the-shelf motors with precision machined masses, and they're mounted 70 degrees from the horizontal. So the CDH, you start off with the IMU and the Raspberry Pi, which has the optical data. So those are our sensor data, and they go to the FPGA using SPI nodes. Inside the FPGA, they take all of that information to an LQR controller, does some math, determines where it needs to go. Then it turns all of that quaternion math to voltages for the ESCs or the speed controllers, and then those power the motors. And lastly, the EPS. We have 4 LiPo batteries in parallel and a voltage regulator that provide power to all of the system. Now to Carter.
Thank you, Christina. I'll now go through some of our critical structural design requirements. So our first critical design requirement was to insulate all of our electrical components. We validated this through our SolidWorks model, and this was done with using standoffs, slots for our cable ties, and Velcro straps, which we hold our batteries. In the detail phase, we verified this through standoffs, slots for our cable ties, and Velcro straps through like a visual inspection and making sure that none of those components moved. This is a checklist showing that all of our components passed that check. Another one of our requirements was that our system was no greater than 7 kilograms. To validate this, we went into our SolidWorks model, assigned values for weight, which were done by the densities of materials, and through this we found our overall weight to be just over 2 kilograms in the SolidWorks model. In our detail phase, we showed and weighed our materials, and it came out to just over 2.3 kilograms. And this was well within our requirement, and we would attenuate that difference to the nuts and bolts that we didn't actually have in our SolidWorks model. Another one of the critical design requirements was that our polycarbonate sheets on which all of our components were mounted did not displace more than 0.5 millimeter. And this was just to ensure that none of our components would have the chance of breaking or deteriorating over time. And in the SolidWorks model, we validated that none of our polycarbonate sheets would move over this distance. In the detail phase, we used dog-bone specimens from the actual polycarbonate sheets that we manufactured and did a tensile test, which proved that our components were that our material was able to withstand such forces. This is a strain stress diagram of that actual dog-bone test to further prove and show us the data that we needed. And this chart is a verification of that data, which shows that we elongated just about 0.024 millimeters, which, as you know, is well within our required amount. And overall, we satisfied all of our critical design requirements. And from that, I'll hand you off to Rachel with ADC.
I'm going to talk about the attitude determination and control system. First, we made an LQR in prelim to simulate how toad should operate. So I'm going to go a little bit in depth on here. So the we use quaternions for this. Quaternions are unit vectors used to describe orientation. So the Q target, which is in pink, that's going to come from our Raspberry Pi. The Q observed up here in the green, that's going to come from our sensors. Those are going to be compared. We're going to find the error between them, and that's going to go into our controller block. Our controller is going to calculate all the torque values for each of our reaction wheels and send that to our actuators block. that sends it to our red blocks. Those simulate real life, so it's simulating our reaction wheels, and it's also simulating real life situations. So we also created some optimized code. We use the fmincon function in MATLAB to minimize our torque values, so that way any rotation that we do will have the most efficient way of getting there. So the control law was completely converted to VHDL. We had to do that for our FPGA. Unfortunately, due to time constraints and difficulties with the IMU, we could not integrate our full VHDL control law with the system. However, in prelim, we were able to satisfy requirement 3.1, which is being within plus or minus 1 degree of error, and requirement 3.2, which is spinning no faster than 15 degrees a second. So our third requirement was that the ADC shall have a maximum mass of 8 kilograms. These are all of the components in the ADC subsystem. These, the 3 kilograms was from the data sheets. That was our theoretical value. Our actual value was about 2.6 kilograms, so we are actually less than the theoretical, which is also less than our maximum allowable. Thus, we satisfied this requirement. One of our other requirements is that the ADC shall calculate the necessary response for their maneuvers. So this was our prelim. You can see that it's showing the torque values. The torque means that we're moving, and when it reaches 0, it stops, and so we are not moving anymore, so we arrived at our desired orientation. And in detail, we did this with our VHDL. We applied a desired orientation right there. We calculated what the final sensed orientation should be, and then we calculated the percent difference between them. So our largest percent difference is 3%, and that's still within our plus or minus 1 degree of error. So our VHDL did work. So some of our major design requirements were satisfied. Unfortunately, we were not able to test requirement 3.1 being within plus or minus 1 degree of error, and requirement 3.2 actually moving at 15 degrees per second or less, but we were able to satisfy requirement 3.4 and 3.5. Now to Jonathan for command and data handling.
Thank you, Rachel. The system of command and data handling handles the data and commands transferred throughout the system. Here we show the critical paths, SPI and PWM, the 3 points of contention where data can be transferred. PWM controlling the speed of the motors, and SPI controlling the actual data. For the Raspberry Pi, we control the transfer of data from the FPGA, telling the user where we are and how we're moving, what our controlled torques, what we think we're doing. That data path is shown here in red. We also allow the Raspberry Pi to send a target quaternion to the LQR controller. This is shown physically with that wire there circled in blue. For the IMU, we also use the SPI interface to send data, shown with the red color here. This collects the data from the IMU, that is including the gyroscope outputs, which are angular velocities, and the accelerometer outputs, which are accelerations. Both of these requirements are tested by verifying that the registers are capable of collecting data from the IMU and holding that data, as well as the user being able to request the data from the registry and read it and change it. Through testing, we were able to show that all of those registers were readable and writable, and this is one excerpt of those registries. Now over to Larson to discuss the remainder of the requirements for CDH.
Thank you, Jonathan. The CDH also had to relay the calculated acceleration values to the actuators in the form of PWM, or pulse width modulation waveforms. To do this, inside the FPGA, we had the path shown here, where we had 4 PWM nodes in parallel that would produce the PWM and send it to the ESCs, which would interpret the PWM into those corresponding voltages to actuate the actuators for their appropriate throttle settings. In detail, we verified this by using an oscilloscope to measure the duty cycles that are being produced. We used a 10% duty cycle, which is the max duty cycle for PWM, and this 10% duty cycle, in our case, represented a maximum forward throttle. The 7.5% duty cycle shown here represented a neutral throttle setting, or zero throttle, and the 5% duty cycle shown there represents the minimum throttle, or in our case, reverse full throttle. Then we also demonstrated a system level reset, a component level reset, and then we showed that if we were to send a PWM duty cycle outside of our range, that it would be brought into the range so that we could continue to communicate with our components. Shown here is a table that demonstrates that all the actual observed duty cycles performed as expected for the commands that we gave them. When we under-commanded the duty cycle, we still got 5%. When we over-commanded, we still got the max of 10%. So all of our duty cycles were within the range, and therefore the system was able to operate with any duty cycle that it was provided. For PWM, we also had to make sure that PWM followed the PWM settings that were required by the ESCs to operate. We showed that it could meet a minimum drive of 1 millisecond, a maximum drive of 2 milliseconds, as well as meet the operational frequency of 50 Hertz with an expected response that was variable depending on the duty cycle needed for the throttle setting we wanted. All of the major design requirements for the CDH subsystem have been satisfied, and the CDH subsystem met all requirements. Now to Tim for EPS.
Thank you, Larson. So the EPS had three main requirements that it needed to meet. The first one is that it must output at least 10 volts to the rest of the system, subsystem, so that they can operate correctly. In prelim, our 4 LiPo batteries, the data sheets from that, we expected 15 total volts from there. And then, as you can see here in detail, we verified that it has 15.3 volts. So it did complete that requirement of having at least 10 volts. Moving on to the second requirement, the EPS needs to be under 2.5 kilograms. Again, from the data sheets with the LiPo batteries and the voltage regulator, we estimated 1.9 kilograms. In detail, we got 1.93. So they were both under the max allowable, as you can see here, with the difference of 0.026. Not bad. Finally, the EPS needs to regulate all the voltage correctly to all the other subsystems so that they work correctly. Everything's smooth there. We gave it a 0.5 volt error tolerance. As you can see here, we have the 4 LiPo batteries in parallel. They're going to produce 15 volts for the rest of the subsystems, and then we have the voltage regulator right there. That's going to cut the 15 volts to 5 volts for the Raspberry Pi to operate properly. And then up top, you can see that we have the IMU. The IMU is going to receive 3.3 volts from the FPGA, which has an internal regulator. Here are actual values that we verified in detail. We have 15.3 volts going to the ESCs, as shown earlier, 5.42 volts going to the Raspberry Pi, which is in that 0.5 volt tolerance, and then 3.29 going to the IMU. So we have completed, verified all of the requirements for the EPS subsystem. And here's to Christina to talk about integration.
Thanks, Tim. So I'm going to go over a couple system level requirements. The first one being that the system should have enough torque to rotate. So in prelim, all of our assumptions for moment of inertia, our torque values from our motors, and our mass of the system allowed us to rotate in our simulations, as you can see here. And then in detail, we tested this by hooking up Toad to a remote controller and providing a voltage to the motors to see if it spun, and it did, so you can see that here. So unfortunately, due to time constraints, we couldn't physically test the control law with the actual physical system. So we couldn't satisfy 3 requirements, and those were 1.3, which said that we could have a control law that would determine our attitude as well as actuate. We could determine our attitude, but we couldn't get that integration part yet. As well as requirement 1.4 and 1.7, which stated that we would be able to orient within 180 seconds, as well as, I can't remember 1.4, but point in a specific, yeah, point at a target. Thank you. So we couldn't physically test that either. But through our preliminary analysis, we could prove that it worked on its own, just not fully integrated. And on to Sam to talk about optics.
Thank you, Tina. So for our optical control algorithm, first we have to read the image. Next, we make the image easier to process by sharpening and grayscaling the image, and we save that to apply analysis to it. When we analyze this image, we first apply a threshold to each pixel to see where the brightest pixels are in the image, and we record those in arrays. The largest array dictates where our centroid is, and by determining the centroid, we can get the vertical and horizontal displacements within the frame, and from that we can get our Euler angles and convert those to a new target quaternion, which we input to the FPGA. As you can see here, this is our testing results for our images. We tested a variety of different positions for our object. You can see that the centroid of the object is marked in red, and the center of the frame is marked in green. And the results of that test are here, where we see that the calculated distances are in blue. That's the distances calculator. The distances calculated by the control law, and the measured distances are what we calculated by hand or measured by hand. As you can see here, all of the points are within a half inch of each other. The error can be attributed to measuring them by hand with a ruler and a tape measure. And lastly, we met some requirements, but we did not meet all of them. We do have enough torque to rotate the system, but since we could not test whether we could orient ourselves and reorient ourselves, we cannot determine actuates reorient with less than 180 seconds and stabilize. We do have a working optical control law. Next is to spike for the conclusion.
Thank you very much. So these kind of sum up some of the lessons we've learned throughout the year. The first of which, you have to know what issues we might be having so we don't get bottlenecked. Because one issue was with the machine shop. We got our drawings in early, but not early enough, and one team took way longer than expected. And so instead of having everything fabricated before spring break, as was planned, we ended up not being able to do so until after spring break. That was for precisely machine reaction wheels, as well as our IMU calibration cube, which brings us to the next point of time. We need to make sure we have enough time at the end of the semester to do our integration and testing, because we're not able to, since we are students, we have other classes, other final projects, exams to focus on as well. And so integrating with such a short amount of time after fabricating so much later than expected did not allow us to have enough, did not allow us to be able to satisfy all of our requirements. In addition, we need to make sure we're able to communicate between team members and subsystems, because there were times throughout the year where we were not all on the same page, which of course is an issue when the goal is to finish it as a team. Finally, for our most critical component, and I think this could probably go to any team, you need to make sure that you spend as much money as possible on the most critical component. For us, that was the IMU. We thought we had spent enough with $1,000, and we got a backup one just in case. However, if we had spent $2,000 perhaps on one instead of $1,000 on two, then we would have had a higher quality IMU and would have higher quality data. And therefore, we would have been able to narrow down the issues earlier and possibly finish our requirements. We would love to thank Dr. Khan for his generous contribution to this project. And we'd also like to acknowledge our advisors, Professor Mangum and Dr. Martin, as well as all the other professors and machinists who assisted us throughout the year. In conclusion, TOAD was able to meet most of both of its objectives and requirements. We will also hopefully be having a demonstration soon after. We forgot to put it in the slides, but we'll hopefully be having a demonstration in the Space Lab soon after this presentation to demonstrate how it works with the remote control. Thank you very much, and do you have any questions?
Great job, everyone. I'm Jody Davis. I'm from NASA Goddard. I think you guys were all very professional, and it's a very interesting project. So, and I know you put in a lot of work. I just have a couple questions. So, not many of the groups showed failed requirements. And what is your plan to either modify and then try to verify, or if you had additional time to try to meet those requirements, because you had some system level and ADC requirements that were failed. Would you try to meet them if you had more time, or would you, in the real world, if you can't meet them, try to justify waivers for those requirements that we can't meet? So what would you do?
We absolutely would try to satisfy them. I think if we honestly had about a week longer, then we might have been able to figure it out. The primary issues we can think of are, one, the IMU was having issues. Now, this could be alleviated through, we have a professor on campus, Dr. Brewer, who assisted us a lot. If we worked with him to calibrate the IMU as precisely as possible, then that would have given us better data. The other possible issue we could think of is that our gains were not large enough in the control law. The ball is imbalanced. There's a heavy side even without our modules on it, and that is a disturbance torque that we did not take into account in our simulation. And so if we could take that into account somehow, or just possibly give it a larger gain, hopefully the motors, which we've demonstrated can move the ball in every orientation, would be able to reach its desired orientation. Just due to time constraints, I think we were not able to reach that point. And then we'd be able to satisfy our requirements, hopefully.
So those good comments on time management and lessons learned, because delays happen, of course, in the real world. And then the only thing I didn't see, I asked the other group, budget, and then one thing I actually didn't think about in the other group, configuration management. What have you guys been doing for documentation?
For
Configuration management, what have you done for configuration management?
We don't have it in these slides. However, that was something that we was required by our advisors. What we did, we made an Excel sheet and then had hyperlink to all the different the part list for all the different broken down subsystems. So the upper level of module 2, lower level, the entire module 1, and then with the part sheet, we also went in depth and had all of our drawing files, which were made by Parker, and broke it down piece by piece. And then we had that verified later through the assignment was called conformity inspection to make sure everything was built to spec.
That's good, thank you.
I was wondering, a few questions. Did you guys place any fail-safe or abort switches into the ops softwares to make sure to rate limit or position limit so that things didn't get out of control and go flying? Was that something you guys considered?
We had many considerations. We did consider them, but we never actually had time to implement those. We had limits within our control law on the torque. However, that did not end up having a limit on the angular velocity or acceleration of the reaction wheels themselves, as they're just trying to get up to the acceleration.
The Raspberry Pi could interface with the registers on the FPGA, so we could manually turn off the PWM signals and zero it out, so it just breaks.
Okay. And then were you able to categorize the offset on the CM and the CG? Was that something you were able to do to see how much off? And so that's part of working the control law.
Well, in SolidWorks, we had it modeled. However, there's things we didn't account for, such as wires, such as nuts and bolts. And so what we did to try to accomplish that was, once we had placed it on the test bed itself, you kind of see it over here. We taped on additional washers as needed until it was sufficiently balanced for our needs.
Okay.
We didn't have a method of modeling it, though, because we weren't sure exactly how the wires were going to
So from a structural standpoint, what we did was we weighed every individual mass by themselves, all the components, and then from that we made an Excel sheet that would calculate the amount of mass we had to add to each side, and then through that we'd say if like the camera was offset a little bit, so we knew we needed to add that amount of mass to the other side as well to get it configured in not only just the X or Y direction, but in the Z as well. Like he said, we had the ball was off center. So we had to try to alleviate that.
Okay. And my last question is, I didn't quite catch what the purpose of the optical system was. Was it for a determination of your attitude, or was it more about like a payload?
It was to be a little bit more accurate. So when it finally stabilizes at its desired orientation, it starts taking snapshots. Where's the? you go to the testing, the one with the tests images, when it's so how it works is it calculates the quaternion as it stands with respect to the camera, and to just be a little bit more accurate, it inputs the new target that it had just calculated in C++ to the control or to the Q target registers on the FPGA, which we have access to. So it's just for that little bit of like win more mentality, is be a little bit more.
So is that then basically just being a coarse and fine attitude adjustments?
Right, so since we're trying to simulate, the end goal is to have something that would track orbital debris, the orbital debris is moving in space, and so we know its general location based off the databases, such as I mentioned, space fence. But since it's moving, we want to verify it, which is what the secondary optical control allows for.
Okay, thank you.
Hi, I'm Sarah Hatch from the Jet Propulsion Laboratory, and space situational awareness and conjunction monitoring and mitigation was a personal baby of mine. And so this is close to my heart. But I kind of didn't quite see the point of the whole project. So you were going to, the idea was that you're going to point at the object and then do what?
Well, due to time and scope, we decided to just focus on that portion that you just mentioned. So the hope is that additional teams and further semesters will take our project and then condense it down to one side, so it's actually a satellite having a counterweight on the other side. From there, they can design a capture mechanism of some sort. That is not entirely our problem, so we'll let them figure it out. And then from there, they'll put it onto the full-blown system and hopefully be able to test it again on the test bed. So we're kind of just trying to be the first part of the puzzle. We're just trying to make the attitude control system so that others can build off of it.
And did you factor in, and I'm guessing you didn't because of the time constraints, but what would happen if one of your gyros failed, and does the control think about that?
We know we can. We did preliminary analysis on it. If one goes out, it's actually easier to just use 2 reaction wheels and let the opposite reaction wheel also just turn off, just due to the configuration. However, we never had time to implement that on our system itself. We did do the analysis to prove that it is possible.
Okay, and somebody mentioned kind of taking the shortest route to wherever you were trying to point.
Yes.
In some instances, the cameras cannot be pointed at the sun, for example. No, that's not a problem in your test situation.
Sure.
But was there thoughts on avoiding keep out zones?
I don't believe so. That is a great point.
We didn't, while we were told that if the stars in the background and the sun might be a problem, we didn't factor that in because within the scope of the test, all we had to do was orient to a white object on a black background. But if we had more time, we would factor in some constraints on how many, like if the array was only like 3 or 4 pixels large, it wouldn't have any bearing on where the object was in space. But at this point, it does not have any constraints for speckled in the background or distances over a certain amount of
Recirculation.
yeah, for certain.
All right, guys. It's a good presentation. I like the system. It was a cool problem to try and solve, especially the control laws for it. Starting with the presentation layout itself, some of the slides were a bit cluttered and a bit visually difficult to handle, shall we say, especially at the beginning. This is bulky, so you had some. I know you had some great animations for some, but that's just purely on the presentation side. So let's talk about your actual project. We brought up the optical tracker. I'm going to bring it up again because I've worked a little bit with optical tracking, and it's quite a difficult problem to solve, and especially I feel like it was a bit glossed over as your end stage control plan, right? Because that's your critical phase. You can roughly get this system where it's going, but that optical tracker is what's going to bring you home, right?
Absolutely.
And I feel like it was a bit glossed over in that as she mentioned, space is not a sterile environment, right? You're going to have a lot of other light sources. And the other thing is, we know within a relatively good tolerance where these things are, but that's very different than knowing what the debris looks like, and that's very different than knowing what its spectral reflectivity is going to look like, what your optical tracker is going to actually be looking for, what its tolerances even are. So you're assuming you know exactly how much light is coming off of this thing and what it's going to look, what it's going to present to your camera, but it could be, it's going to be spinning, it's going to be flashing, it's going to be doing all kinds of crazy things. So the optical tracker is a very difficult problem to solve. Did you think about what you're going to do as far as target identification with the optical tracker?
While it was mentioned to us that most of the objects in space are not perfect circles, because we had so little time and we were already doing our own crash courses in SPI communication and optics and convolution and linear algebra, we decided to simplify the problem down way to the bare minimum. But if we did have enough time, we would account for the less sterile environment of space. But that's not something that we accounted for.
As a quick question, actually, what would you recommend for, if a team would take over this project, what would you recommend for that, for those requirements?
For that, the main thing that you're going to have to do, and what a lot of teams are doing right now, is basically a machine learning machine. Is we're going to go and we're going to look at a lot of space debris. You know, we're going to look at all the video we have. We're going to look at anything anything that the ISS has seen, anything that we've seen from any satellites. What do things look like when they're spinning in space? What does debris look like? So that you have a system on board that's ready to go with that. That's saying, that's a star, that's not a star. You know, right? And that's kind of what you want to do in maturing that tracker.
Thank you.
The other thing that I had that's just kind of a question that popped up in my head here. Can you go to slide 56? Right.
We have mismatching slides.
Sure. This might work. I might just thought incorrectly. What I'm looking for is the duty cycle and the 3.75% duty cycle trigger. There it is. 55. My apologies. So you normalize your upper and lower ranges to fall within your max and your min. What is the lowest level that's going to trigger it? My concern here is system noise. Is noise going to trigger your system and say, oh, that's my expected lower level duty cycle? Was there protection put in place for that to make sure that there weren't inadvertent triggers because you were normalizing something that you shouldn't be?
It's not truly a normalization, it's more like a saturation. So if the FPGA attempts to control a 3.75% duty cycle, or the control attempts to control it, the FPGA says, no, you're going to control 5%, don't care what you're saying. Same thing for the upper bound of 12.5% or anything higher than that. In terms of line noise, we didn't account for that. It's a good suggestion that we should account for. Do you have any suggestions on how to account for line noise?
Not many. I thankfully am not a double E, but but I do know it can wreak some serious havoc with the system. So just something maybe consider.
There's a value and a persistence of that value usually. That's kind of where you start with. So you set a boundary value condition and say, shorter than this, if it's longer than this, and do something about it. So that's kind of where you start, but every controller is different in how you work with it.
If we had the honor of having an E on our team, we would have decided to have the ESCs built for us rather than choosing one off the market, as that's one value we want to control. It's how we actually, we're controlling the speed through the ESCs, but we're trying to control an acceleration, producing a torque. So if we were able to design the system of the ESC to produce that torque accurately, then we might be able to get a more desirable system. Is there anything else on that topic?
No, that's all I've got, guys. Good work.
I was interested in the lack of satisfaction of some of the more dynamic measurements. I just wondered if that was, we didn't have the equipment or didn't have the time, back on page 46. The static measurements were fine, but the dynamic ones you couldn't quite satisfy. And were those not satisfied, you just didn't know?
We couldn't prove it. I mean, it worked in simulation. It worked on Simulink, it worked on VHDL, but we weren't able to verify it when we integrated everything into the physical system.
Yeah.
So,
Understood.
we like to think it